So this is the truth table that we derived a few videos back for the counter that we want to design. And in the previous video, we said the way we want to design a counter is to somehow use the present state to give us uh, t, the t inputs to your flip-flops so that you get this next state, right? So, so let's make another column here and call this flip-flop inputs. So we want to decide how we are going to get these appropriate flip-flop inputs. And there are two flip-flops, so we have two. So let's two inputs. Let's call it TA1 and TA0. Okay. Now, if you want, your so if you have a present state of 0 and your next state is also 0, okay, what should your t input be? Of course 0, right? That's how a t flip-flop works. When the input is 0, the t flip-flop does not change its state. So what we want is 0 here. Now, if your input is 0 and you want to change its state to 1, what do you want? You want a change of state. So you want ta0 to be 1. Similarly, you can see that you want a 1 here and you want a 1 here. Both the inputs should be 1 because you want both the inputs a1 and a0 to change, to switch, right? So you get 1 1 here. And similarly, in this case, you don't want a transition in A1, but you want a transition in A0. So if you don't want a transition, you have 0. And if you want a transition, you need to have your TS1. In the final case, you want transitions in both the bits. So you want 1 1 to be here. Okay. Now, as we said before, what do we need to design? We need to design a sequential circuit which takes as its inputs the present state A1 and A0 and gives as its output TA1 and TA0. Sorry, this is a combinational circuit, right? So if we can do that, then we can connect. We know what the T inputs are going to be, how we get those T inputs, and we can put that together. So let's try to get TA1 and TA0. Now this is very straightforward, right? You can simplify and you can get a Boolean algebra using the K-maps. So it's just a two input K-map. Let's write A1 here, let's write A0 here, and let's say this is for T A1. So 0, 1, 0, 1. So where are the ones in this case? So for TA1, you have 0, and then you have uh, A1 is 0, so A0 is 1, so 1, and then 1, 0 is 0, and then 1. Okay, and you can group these two ones together and you can write the Boolean expression as TA1 will be equal to what? Basically, you eliminate A1 and it becomes equal to A0, right? So TA1 is equal to A0. So whatever A0 is, T1 is going to take that value. TA1 is going to take that value. Now let's try to do the same thing for TA0. So let's try to draw another K-map here. And this particular K-map is for TA0. So you have A1 and A0. The values are 0, 1, 0, 1. So you can see from here what you get. You have all ones. Well, you don't even need to write the K-map, right? You can just say, just by observation, that TA0 is always going to be equal to 1. Okay. So if we have this, so the two Boolean expressions that we got was TA1 equal to A0 and TA0 equal to 1. Now let's draw the two flip-flops. So you have clock, you have TA1, let's say Q1, Q1 bar, right? And then you have, this is the clock, sorry, TA0, Q0, Q0 bar. Now, what is connected to TA1? What we do is you have to connect A0. So this is your present state, right? You connect this to TA1. What is connected to TA0? Just 1. And then you connect the clocks. Okay, so to a clock input, let's say, and your state is this. These are your outputs. So this is your A1 and this is your A0. And now if you run this circuit, you would see that the state changes from, so it does the counting that we were talking about. And in the next video, let's look at a multi-sim simulation to see whether this works as expected or not.